Molecules can be represented in a variety of ways, in formulas and figures. To illustrate, let's first consider nitrogen, the major component of Earth's atmosphere. Nitrogen gas is composed of only one element, the element nitrogen. It is a diatomic molecule, so its molecular formula is N2, a molecule with molecular mass of 28. The spatial character of the molecule is represented by showing the nitrogen molecule in a ball and stick representation. A more faithful representation is the space-filling model, in which the atoms are shown as spheres of a size that they appear to have when they encounter other molecules in collisions. The radius of the nitrogen atom in this model, sometimes called the van der Waals radius, is larger than the covalent bonding radius. Thus, the surfaces of the two bonded nitrogen atoms overlap considerably. Now, let's consider a more complex but familiar substance. Aspirin, a widely used pain reliever, is an organic substance made up of carbon, hydrogen, and oxygen. By use of combustion analysis, it is possible to determine the weight percentages of carbon, hydrogen, and oxygen in the compound. From such analysis, the empirical formula is found to be C9H8O4. Measurements show that the aspirin molecule has a molecular mass of 180 atomic mass units. This mass corresponds to the formula C9H8O4. Thus, the empirical formula is also the molecular formula. Experiments reveal that the atoms of the aspirin molecule are connected as shown in the Lewis structure. The hexagonal ring of carbon atoms connected by alternating double bonds is called the benzene ring. Two carbon atoms of the ring are connected to the other groupings of atoms. The top one is called our carboxyl group. The other is called the acetyl group. The traditional organic chemical name for aspirin is acetylsalicylic acid. The ball and stick and space-filling models for aspirin show the three-dimensional relationships between the atoms. Notice that the acetyl group is twisted somewhat, so that the oxygen atom bound to the carbon can lie out of the plane of the benzene ring.